Okay, so hello everyone, welcome to this extra session. Today we are going to talk about Hausdorff measure and length. So, okay, so basically there are some natural questions one can ask at first. So let me start with some natural questions. So, so the first thing is basically what is wrong with the Lebesgue measure. So, so what is wrong with Lebesgue measure? Okay, so from the Lebesgue measure, we knew that if we have an arbitrary looking set, we have a notion of Lebesgue measure, which generalizes our notion of length in R and area in R2 beyond just straight lines or let us say rectangles or triangles. Okay, so Lebesgue measure generalizes this notion. The problem is that if we are living in R2 or say in Rn for that matter, we can never talk about a one-dimensional measure or size of object using the Lebesgue measure, okay? Because uh, something which does not have area will be so in R2 which something does not have area will be two-dimensional Lebesgue measure as zero. Okay, so you see this is what I want to mention. So so the problem with measure is that if if we are if we are in R2 or for that matter let us say Rn, uh, we can never talk about one dimensional measure or size of object using Lebesgue measure. Okay, so because of the thing is that because the L2 measure of x is zero whenever, so let us say x is a uh, x which does not have area. So x is something like set which does not have area. Okay, so because of this this Lebesgue measure is not suitable for studying curves in R2. Okay, so it is not suitable for curves in R2, let alone studying arbitrary subsets in let alone studying. Okay, fine. So basically to study the one dimensional size of the set, one has to look for something new, and Hausdorff measure is one such thing. Okay, uh, and it works in arbitrary metric spaces. So we'll move to that one and we'll make some settings. Or initial setting is okay. So wait. So Okay, so let me just write it down. To study uh, a one-dimensional size of the set, uh, one has to look for something new, and Hausdorff measure is one such. There are some other notions of measure also, but for this one, we are going to talk about Hausdorff measure. Is one way of doing it. Okay. Okay, fine. So we'll now talk about Hausdorff measure. Okay. And so the natural question would be, since we are talking about curve, this question two here is that. So let us say, okay, I will make this thing precise later, but just at the first stage, let us say this is a one-dimensional Hausdorff measure. So does H1 agree with the actual notion of the length of the curve? Actual notion of the length of the curve. Okay. So the answer to this is yes. As the title also suggests, we are going to see this one. Okay. And also we can talk about in integrability of function with respect to the Hausdorff measure. So that is not the part of this one. Yeah. Uh, I will mention the references where one can find the introduction on the Hausdorff measure later on. So we'll move to the definition of Hausdorff measure. Okay. Okay. So yeah. Let us make first some basic setting. Okay. So let x comma d be a metric space. Metric space and A is any subset of X. So there's no restriction on A. Uh, we we shall define the S dimensional Hausdorff measure of set A. Okay, so okay, so where S is basically 0 to infinity. Uh, okay, so yeah, so S is basically 0 to infinity. So definition is just keep in mind the way we define the Lebesgue measure using the covering by the balls and just taking the volume of the ball and taking the infimum over all those coverings, summation of the like volume of the ball and taking the infimum over all those coverings. Okay, something similar we are going to do, but at the place of elementary sets we are going to consider some other coverings. Okay, in general coverings. So let us denote this notion Hs delta A. This is defined as infimum of summation I equals to 1 to infinity diameter of Ei to the power S. Okay, and where infimum is taken over taken over all countable covering of A. Okay, that is basically A is subset of union of this is I equals to 1 to infinity. Okay, with so where this delta so what is the role of delta? So basically we are not just taking a arbitrary this one covering, this diameter should always be less than equals to delta for every I. So basically what delta do is that it puts a bound on how big the covering set can be. How big the covering set can be. Okay, so observe that a smaller delta gives you a bigger this one, which is delta A. Okay, because once you make delta very small, and then you can take the diameter of this one is getting small, and you take the summation and you take the infimum over all these coverings where the diameter is basically uh, uh, now less than delta, let us say delta naught, which is less than delta. Okay, so you will already give a, so earlier you have a covering for a diameter less than delta, now you have more covering. Okay, so if we want to draw, if we want to see, so like smaller delta positive, I mean there's a proof of this one, I will mention in A. Okay, so it means that if we draw a graph, let us say this is delta and this is just delta A. So here let us freeze our A and S. Okay, so this is basically this is a graph of this will be non-increasing. Okay, so what we do now is, so this observation will be our definition for S dimensional Hausdorff measure of E. So this is your uh, S dimensional Hausdorff measure. Okay, which is defined as uh, this is limit delta goes to 0 h as delta A, which is nothing but supremum over all delta positive A. Okay, so this could be possibly infinite, possibly infinite.
Sorry, can you reshare this? Okay, yeah, it's visual.
Sorry, Ravi, anything?
Yeah, yeah. No, no, it's fine.
Okay, so this is known as the S dimensional Hausdorff measure of a set A. Okay, so I'll just mention some properties for the proof. One can go through the reference, which I will mention. Okay, so I hope this definition is clear. Okay, is it fine? Okay, to mention some remark. Okay, so basically, uh, HS. So this is actually an outer measure. Okay, uh, so basically, what we're talking about, it is on its measurable set, it is a measure. Okay, measurable set forms a sigma algebra, and when one one restrict it to its measurable set, It is a measure. Okay. But whether it is a useful measure, yes, because it's a Borel measurable. Uh, uh, so basically, it is a Borel measurable function. It means that every Borel set is so. It means that every Borel set is HS measurable. Okay. Uh, we have more things like it is a regular measure also. It means that it is a Borel regular. It means that if you take any arbitrary set that is contained in a Borel set, so that the Hausdorff measure is basically equal. Okay. So uh, HS is basically Borel regular. So it has a lot of nice properties. Okay. Yeah, and the important thing is this is quite important. So let us say if we are sitting in, let us say Rn. Okay, so now let us say we are in Rn. If A is a subset of Rn, okay, and we take S is equals to n. Okay, so what do we have is that the n-dimensional Hausdorff measure of A is nothing but basically there will be some constant, and it is nothing but the Lebesgue measure, n-dimensional Lebesgue measure of this set A. Okay, so once we talk about n-dimensional Hausdorff measure of a set A, we have the equality with Lebesgue measure. Okay. Okay. Sixth point is uh, there exists a unique S naught belonging to 0 comma infinity, uh, such that Hs of A is equals to 0 if S is S if S is greater than S naught, and Hs S dimensional Hausdorff measure of this one is infinity if S is less than S naught. Okay, so basically this is kind of a critical value. Sorry, this is kind of critical point of this Hausdorff S dimensional Hausdorff measure. So if you just draw see the comparison between these two, let's say we have somewhere here S naught. So after this it is 0, and after this it is basically before this it is basically infinite. So at this point S naught, it can be like at S naught, it can be 0, finite, or infinity. We'll see some examples of this one. 0, finite, and 0, finite, or infinity. Okay. Okay, but anyway, this says that every set has a reasonable dimension to be used in the Hausdorff measure sense. Okay, so basically, it says that what we want is this one only. It okay. So this says that okay, I haven't defined. Okay, yeah. So okay, this says that every set has one reasonable reasonable dimension to be used. I will tell why I'm saying this dimension word is coming here. To be used in Hausdorff measure. So I should write this six as a like kind of this is a theorem. This is a kind of I mean all these things are theorem. Like one has to prove it. This is important for us, point 6, because this will give us the dimension of the set S, the set A. Okay, fine. We will now talk about the Hausdorff dimension. Okay, so if S naught is finite, finite number, let us say, not positive infinity, we call uh, we call we call this. Okay, so if S naught in the property 6, okay, so in this property 6, this S naught, if it is finite, and if it is finite, uh, but it is not infinity, okay, so if it is finite number, not positive infinity, we call this S naught the Hausdorff dimension of the set S, set A. Hausdorff dimension of set A. Okay, so basically, the way so Hausdorff dimension, let us denote it by this. A is nothing but supremum of all S, such that S S dimensional Hausdorff measure of A is basically infinity, which is same as infimum of all S, such that Hausdorff measure of A is basically 0, and which is nothing but S naught. Okay, so I hope it is clear.
Is there example where S naught is infinite?
Yeah, I will talk about all those things.
Okay.
So at first place we have some observations. So this is like just wait a minute. Yeah. So, so observation is so one observation is, let us say, if there exists some S star such that S S star dimensional Hausdorff measure of A is basically bounded by some positive constant m, then what does it mean? Can anyone tell me?
Dimension should be less than S star, less than or equal to.
Yeah, so you mean the dimension, the Hausdorff dimension of A should be less than S star.
Yeah.
So then uh, this means that the Hausdorff dimension of A should be less than equals to S star. Okay, and the similar thing, if there exists some uh, uh, let us say m1, sorry, S star, and let us say m, okay, m1 such that this Hausdorff measure of A is basically greater than m1, then this means that dimension of Hausdorff dimension of A is basically greater than equals to S star. Okay, so means if you just bound your Hausdorff measure between two finite quantities, that S star is going to be the dimension of that one. Means if there exists an S star such that HSA is positive and finite, so it means that if there is there exists a S star such that basically H star of A is positive and finite, then basically the Hausdorff dimension of A is nothing but S star. Okay, so yes, Ravi, what was your question? Whether S naught can be infinity or like what was your
Right.
question?
Is there an example where S naught is infinite?
S naught means the Hausdorff dimension is infinite.
Yeah,
Uh, Basically, I'm
because
defining S naught
uh,
so that it is not positive infinity.
I see. But if you go to previous page, your S
Yeah,
naught is from zero to close infinity, right?
yeah,
So you wrote there is this unique S naught which can be infinity. So I just wanna know for which type of a S naught is infinity.
yeah. Okay. So
Here
if
A is a
S naught
subset
is
of
yeah, yeah.
Rn.
So if S naught is infinity, it means that the Hausdorff measure
Mhm.
for every S is basically infinite, isn't it?
Right.
For every S, it is infinite. Hausdorff measure.
Yeah. Yeah, but A is a
Uh,
subset of Rn, right?
yeah, A is a subset of Rn. So I I don't think that could be.
Uh, yeah, I don't think it is possible.
Yeah,
Means
it is
infinity
possible.
may not.
There will be some. Okay, yeah, because the let us say because we have the okay. So if we are sitting A in Rn, okay,
Mhm.
at
Mhm.
least its n-dimensional Hausdorff measure is nothing but its Lebesgue measure.
Yeah, right.
Okay, so
So it's Hausdorff dimension at most 10.
yeah,
Means, yeah.
yeah, exactly. So
So I think we may exclude infinity in
yeah,
this.
I think
I
we can
don't.
exclude because yeah, don't think this will be possible here.
At least if we are in Euclidean case, I don't know about arbitrary space.
Arbitrary metric space also I because arbitrary metric space the same thing will follow like the
Right.
same thing will
Right.
happen, but we have to see. But in the definition, it is included. So
Okay.
I think it will be some kind of weird kind of thing. I don't know what.
Okay.
Because the only thing is we have this HSA will be infinity throughout, and this is quite
Right.
yeah,
Unnatural.
yeah, it is quite. Anyway, I will see and let you know. Okay,
Yes.
this is fine. So yeah, we can talk about just a small example. So this set of real number has uh, Hausdorff dimension is equals to 1, but uh, 1 of R is basically infinity. So basically, it says that at the critical point we have the infinity. So basically, for this one, it is 0, S is 1, infinity if S is equals to 1, and obviously S is less than 1, then it is always infinity. Okay, this is one example, and we will talk about some more examples. So we'll talk about Cantor set examples. So I will start with that one. So we'll talk about Cantor sets and their Hausdorff measure and dimension. Okay, so I will talk about a generalized. No, okay, no, I should not say generalized Cantor set because that is depends upon other things. But okay, so I will talk about C lambda, where lambda is basically 0 to 1 by 2. Okay, and what we are going to do is we are going to remove the intervals. Okay, the same way which we do for the standard Cantor set, means 1 by third Cantor set. Okay, so at the first instance we have this interval, okay, 0 comma 1. So this is at the first stage, 0 at the 0 stage. This is our interval. We will divide this interval into two parts. Basically what we are going to do is uh, lambda length interval we are removing from the middle, and we are left with two intervals, this one. Okay, so basically it is like we have this one. Wait. So we have this one. This is our I. This is our I 0 comma 1. What we are doing is, once we remove, we are left with these two intervals. Okay, so this is at the first stage. We have this interval I 1 1 and I 1 2. Okay, so if we continue this process, basically inductively, uh, if if 2 to the power, so just observe that in each, so like at the 0 stage we have one interval, at the first stage we have two intervals, at the third stage we will be having 2 to the power sorry, at the third, okay, sorry, at the first stage, at the second stage we will be having four intervals, and the third stage we will be having 2 to the power 3 intervals, and so on. So inductively, if 2 to the power k minus 1 intervals, let us say we are writing I k minus 1. So this is at the k minus 1th stage. Okay, first interval k 1 minus 1, so stage k minus 1, second interval, and so on, and stage. So how many intervals are there? 2 to the power k minus 1 at the k minus 1 stage. Okay, this one, each having length lambda to the power k minus 1, have been constructed from the parent interval. So parent interval means, so see, earlier this was the parent interval, this one. After the after the first stage we have two parent interval. Okay, so means the earlier stage intervals are called the parent interval for other intervals. Okay, the next stage interval. So length lambda to the k minus 1 have been constructed. Then we define I k comma 1, I k comma 2, and so on, I k comma 2 to the power k, by, so this is by deleting an interval of length 1 minus 2 lambda, and into the diameter of, basically the basically, so this is basically at the k and k minus 1 stage jth interval. Okay, so this is nothing but 1 minus 2 into lambda to the power k minus 1, because the length of these intervals are nothing but lambda to the power k minus 1. So from the middle of each parent interval. Okay, of the earlier cities. So we thus obtained of the power k intervals this obtained at kth step. At the kth step, and this have length lambda to the power k. Okay. If you're feeling difficulty while understanding this one, just keep the mind of just keep the recall of this 1/3 Cantor set. Okay, the way it has been constructed. Okay, fine. So okay, so yeah. So now how do we define? So we set C lambda is nothing but we define the C lambda as the section k equals to 0 to infinity and union 2 to the power k. Oh, sorry. Union 2 to the power k I k j. Okay. So again, the construction looks like this one, and again you have some interval removed here and here, and this will like this process will follow. Okay, so basically this C lambda is again what we know. It has these properties: compact, non-empty, perfect, and therefore it is uncountable, and perfect Lebesgue measure 0. All the properties of this 1/3 Cantor set. Okay, so this is known as the in general Cantor set. C lambda is a this is our Cantor set, and basically C1 by 3 is our middle third Cantor set. Okay, so we'll now talk about its Hausdorff measure and dimension. So whether the construction is clear, I hope it will be clear to everyone. Okay, so measure and dimension. Okay, so observe that for every k is 1, 2, and so on. So basically, this C lambda is contained in this union 1 to 2 to the power k I k j. Okay, and so for s is in between 0 to infinity, what we have is hs lambda k of C lambda is basically less than or equals to summation I equals to 1 to 2 to the power k and diameter of I k j to the power s. Okay, so what is this? This is basically going to be, so diameter of I k j is what? So lambda to the power k. So this is nothing but 2 to the power k into lambda to the power k into s. So this we can basically write it as 2 lambda to the power s to the power whole power k. Okay, so this upper bound has to make useful we need this upper bound to remain bounded as k tends to infinity. Okay, so for this, okay, so so for this upper bound to be useful as k tends to infinity, it should remain bounded. Okay, okay, and this happens if basically 2 lambda to the power, wait a minute, yeah, 2 lambda to the power s is basically less than or equals to 1, and this will gives that s is less than or equals to log 2 upon log 1 by lambda. Okay, so now let us take s naught to be log 2 by log 1 upon lambda. Okay, so for this s naught, what would be the Hausdorff measure of this one? So this we can take it as limit k tends to infinity hs naught lambda to the power k c lambda, which is nothing but less than or equals to 1. Okay, so thus, as I said earlier, so thus a Hausdorff dimension of this c lambda is nothing but less than or equals to s naught. Okay, so this was kind of an easy way from to get the upper bound. Lower bound, to get the lower bound is kind of little bit constructive. So I will just write the lower bound. I will not mention the proof because time restriction. So the next thing basically is to show hs naught of c lambda is basically greater than equals to 1 by 4. And hence, what does it mean? Uh, can anyone tell me? What does this mean? So we have hs naught of c lambda is greater than 1 by 4 and less than equals to 1. Can anyone tell me? Okay, so basically the Hausdorff dimension of this c lambda is s naught is log 2 log 1 by lambda. So I hope it is clear. Fine. And actually, basically in the book in which the proof is there, I haven't seen what would be the what would be the uh, I have to check this one. What would be the exact Hausdorff measure of C lambda? I think uh, it uh, it is it is 1. Okay. This okay. Let me just put it as an exercise to check. Okay. Anyway, so yeah. So I hope it is clear. So basically, the Hausdorff dimension of this one is basically sorry, is not an integer. So what would be the Hausdorff dimension of the 1/3 Cantor set? It will be 1 upon 3, and this will go there. So, yeah. Is it clear? Basically, here, basically, this also reflects in a nicer way the size of C lambda. Like, nice, by nicer, I mean in a natural way. Basically, it says that uh, when lambda increases basically the size of deleted holes decreases, and and the set C lambda becomes larger, and and dimension, Hausdorff dimension of C lambda increases. So uh, basically, if we converge to 1 by 2 from the left, it is nothing. So S will go to 1, and if lambda goes to 0 from the right, S will also go to 0. Since this is continuous, HS is continuous with respect to this this S. What does it mean? That it means that for every S belongs to 0, 1, there exists a Cantor set uh, with with Hausdorff dimension. Equals to S. Okay, this is one such examples, and so there is notion of generalization of this Cantor set. Basically, we will not take a sequence of points. Like for Cantor 1/3 set, the sequence is 1 by 3, 1 by 3, and 1 by 3 square, and those things. So we will not take a sequence of this the sequence of numbers in 0, 1, and through which we will define the Cantor set. Also, there are generalization of Cantor sets in higher dimension in Rn. Basically, what we do in that, when we take a square and we start removing squares in the middle from this one, and then again in this one we start removing some squares. Okay, so one can start with square, or one can start with circle and then start removing some circles. So yeah, so like we have the generalization of Cantor sets in R, and these are like quite interesting once we talk about the Hausdorff dimension and measure. Okay, I will mention the reference where one can go and see all these things. Okay, now we will talk about the important aspect of this one. I don't think I would be able to prove it, but anyway, let me just quickly mention. So, because this will lead to some surprising things. Hausdorff measure and length. Okay, so uh, let me write it as a theorem. I will add two parts so that it would be easy to use. Theorem 1, theorem 2. You have to see with it. So let X be a metric space, and gamma such that A comma B to X is X is injective, and let us say Lipset. Then basically the Hausdorff one dimensional measure of this set gamma A comma B is nothing but the gamma of A comma B is nothing but the length of the curve gamma. Okay, so this is the result which we will. This is kind of a very uh, kind of very good. So this is also, so this result is there in more general setting, that is known as simple curve. Means every pre-image has pre-image of every point is an interval. For that one also it holds, but I need only for injective and Lipset maths. Uh, so basically, Hausdorff one measure basically gives the length. Okay, so it is kind of one dimensional. This curve is one dimensional in the Hausdorff sense. Okay. Okay. Uh, let us see some application of this one. Okay, so let us talk about a Jordan curve in C, which is so Jordan curve in C means it is homeomorphic to a circle and is compact. Okay. Let gamma be a okay. By the way, here is one question. Let me just mention. So, so suppose gamma says that a comma b to x is injective and rectifiable, and let us say LD of gamma is finite. Okay, and LD of gamma is finite. Take the arc length parametrization. Arc length parametrization. Parametrization. Let us say gamma s. So gamma s is from 0 to LD of gamma and to x. Okay, so since gamma is injective, can we say gamma s is also injective? So basically, gamma is nothing but gamma s composition s. Okay, so where recall where s is from a comma b to uh, LD of gamma is defined as S of t is basically length of the curve gamma restricted to the interval a comma t. Okay, so here our curve gamma is injective. Can we say that the curve gamma s is also injective? Anyone? Recall that s is always increasing. This is small s is increasing. And yeah, so
And then it should be, I think.
sorry, Ravi, what?
Yeah, it should be injective then gamma s.
Yeah, yeah, because this gamma is injective, so this s will be strictly increasing, isn't it? No, so sorry. So this okay, yeah. So this gamma is injective, and this s is basically increasing function. And for that matter, this gamma s has to be injective, so that whenever the injectivity fails for gamma s, it will fail for gamma, isn't it?
Yeah.
So means, and also we have seen that this gamma s is one, let's say. So you have you might have observed now why I've written this one in this form, because I'm going to use this one. So let yeah so let okay, so let me write it as a section wise. Okay, I will just take uh, 6 to 7 minutes. So let gamma be a Jordan curve in C. Okay, so we have two things now. Either gamma is rectifiable that is LD of okay sorry L Euclidean of this gamma is less than infinity, or this is basically non-rectifiable, which is a Euclidean length of gamma is basically okay. So we have two cases. So first, suppose that gamma is rectifiable. Suppose LD of this gamma is rectifiable. Uh, okay, and So the wait a minute. Am I audible? Hello.
Yeah.
Okay. Okay. So LD of gamma is less than infinity, and take the oh, sorry, wait. So I want to mention the Osgood result. So just write it down. Osgood curve. So this is basically, let me just write it down, the reference. Uh, a Jordan curve of positive area. Okay. Okay. So it says that there exists a non-rectifiable Jordan curve gamma in C, such that this L2 sort of gamma is basically positive. This is quite surprising. Uh, we have a non-rectifiable Jordan curve, so that this L2 of gamma is positive and finite. Okay, so what does it mean? It means that is this two-dimensional Hausdorff measure of this curve gamma is positive and finite. Okay, and this says that basically the Hausdorff dimension of this curve gamma is 2. Okay, it's a kind of two-dimensional curve. Okay, so it means that Hs gamma of this Osgood curve is 2, positive and finite, when S is equals to 2, and when S is less than 2, it is infinity. Okay, and also if we have a rectifiable Jordan curve, that the Lebesgue measure is always going to be 0. So basically uh, Lebesgue two-dimensional Lebesgue measure of rectifiable. I think this is true for any rectifiable curve, but I will write it for Jordan curve because I think the area inequality will satisfy that one. Isoperimetric area inequality is there, through which one can prove that basically the Lebesgue measure is going to be 0. But anyway, just to compare for Jordan curve, C is 0. So what does it mean? It means that the Hausdorff measure of this one okay, wait a minute. So Hausdorff one measure will be Hausdorff two measure will be okay. So S is equals to 2 is equals to 0, and wait a minute. So okay, yeah. So it's a Jordan curve. It is injective, like it is a, but the endpoint it is not injective. But that will not really matter here. Basically, we can just take the, we can just remove the endpoint and just take any other thing. So, uh, so by the earlier known result, we take the arc length parametrization of this Jordan curve. So one dimensional Hausdorff measure is now going to, because this This is a parameterization of that one, so it is going to be this one of the image set, and this is nothing but the length of the curve gamma by the by 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 this result, theorem 1. And it means that, so, and this is, since it is rectifiable, it is finite and positive. Okay, so it means that the Hausdorff dimension of this curve gamma is basically 1. Okay, and Hausdorff measure will be, so this is one such section where we are talking about the Hausdorff measure of curve. What about the Hausdorff measure of the boundary of a domain? Okay, some results are there in that section, but I will just mention a paper. Uh, I'll just mention a paper. If anyone is interested, one can go to this one. So it is related to boundary of a domain omega. So to to come up with some good estimates for the Hausdorff dimension of this boundary of the boundary of the domain, we need some metric and growth on that metric in the domain. Okay, so I will just put a reference because I don't think I will be cover this one. I will be able to cover this one. So Jones and this is basically density property of harmonic measure. So this is kind of paper, old paper, but you can find a lot of interesting stuffs in this one. Okay, so as I said, let me just mention a result which says that, so let us say omega subset of R2 satisfies growth condition with respect to, so this is simply connected domain, simply connected with respect to the hyperbolic metric. Then basically this Hausdorff dimension of the boundary of omega is less than equals to 2 minus some constant will be there, and satisfies logarithmic growth condition, log growth condition. It means that the hyperbolic metric satisfies x naught comma x is less than equals to 1 upon alpha log 1 upon del omega x plus c. So alpha, this will be there. So yeah, so the dimension of, so Hausdorff dimension of this one will be less than 2 only. This constant c depends upon the dimension n. I've written in particular for 2, so let me just write it down as c only. So it is c into alpha. Okay, yeah. This result is there in other paper, but so this result is there in general setting like for Rn, but in this paper one can find for simply connected domains in the plane the estimate for Hausdorff dimension. Okay, yeah. So I will stop here. Any question?
Yeah, so in Rn, this Kobayashi metric will always satisfy this log growth condition, right?
No, I mean
For convex domain,
uh,
convex domain in CN.
uh, symmetric on convex domains.
Yeah, I think for that
No,
the Kobayashi metric will satisfy.
but in that case, every Kobayashi domain will be Goldilocks because the other condition will. Okay, oh, no, wait.
No, not every convex domains are Goldilocks.
Yeah, second condition will fail.
Yeah, means I am saying convex domain in CN will and Kobayashi metric will satisfy this log growth. I think so.
Yeah, I also think so. I mean, it
Because
seems
there I
because of the because anyway, the cusp kind of thing will not be there because of the growth condition.
Yeah, or assume it has a visibility, then maybe it alpha is to something. Yeah.
Yeah, yeah. Okay,
Okay.
yes, yes, yes.
Yeah.
It is, yeah,
Assume.
1 by 2 log or something is there.
Right. Right.
Yeah,
Yeah. It is true for all convex domain.
yeah, yeah. But here
So.
I want to mention that I have not seen any result on the
Mhm.
boundary of a domain, result on the dimension on the boundary of the domain under the assumption on the growth condition of the Kobayashi metric. I don't know whether it has any application in that setting or not, but I
I see.
haven't seen any result.
I see. So you are saying if there is a growth in Kobayashi,
Metric, does it give
you
any,
are
yeah, does it give
information on a
any
boundary.
volume of the
I,
boundary or the
I
Hausdorff
see.
dimension, or there is also one more notion of dimension called Minkowski dimension.
Mhm.
So I
Okay.
have not seen any result of this kind. Maybe it will be,
I,
it is there, but I have not seen. Yeah.
okay. Mhm. Thank you.